In the previous lessons, we learned about equilibrium and how a chemical reaction over time, especially a reversible chemical reaction, over time achieve equilibrium. And this is being described by these two graphs right here. And in any chemical reaction, of course, we always start with reactant. And of course, if we look at this graph, it's concentration versus time. Now, what is concentration? Concentration is basically molarity, and molarity always have this unit. It's the number of moles per liter. And of course, over time, you start with a lot of reactant, a lot of raw materials, and those reactant will react to make product. And it makes sense that you have very little product at the beginning. In this case, you are making more product to the point that you have more product compared to the reactant. But that doesn't really matter. The most important part is where equilibrium occurs. Notice how the concentration of reactant and product does not change. And that is because over time, when you make enough product, those products will react with each other and break down and make reactant again. That's why they call it reversible reaction. Over here we have the same situation where we have reactant make product. But in this case, it is making less product than the reactant. So that's the reason why you have this concentration of product at equilibrium is a lot smaller. So it doesn't matter what graph you have. You make more product or less product, but the characteristic of equilibrium is still the same. That is, look at the concentration of reactant and the product at equilibrium. It doesn't change, right? That is because the rate of making the product is now equal to the rate of making the reactant. And that's the reason why equilibrium graphs are looking like this. In this lesson, we are going to learn how to calculate for the concentration of substances in a chemical reaction at equilibrium. So of course we always start with a chemical equation. And one of the most important things is that this needs to be a balanced chemical equation, okay? So here is the problem that is describing this chemical reaction. Well, after a mole sample HI is placed into a container 1 liter, that's very important because molarity is at 1 liter, okay? At 700 K, the reaction represented above occurs. So here we have this graph that represents this chemical reaction, okay? Now, the concentration of HI as a function of time is shown below. So this here is a graph that represents this reaction, and it is going to be at equilibrium at this point right there. You see that right there? How HI does not change in terms of concentration. But what is HI? Of course, this is your reactant right there. So keep that in mind. And we are given the specific values of concentration. Notice how this is number of mole over 1 liter. That is very important. If you don't have 1 liter, you have to make it at 1 liter. Change everything to molarity. So in this case, write the expression for equilibrium constant for K for the reaction. So that's pretty easy. You just need to realize that K in general term is always product or product over the reaction. And it's more complicated than that, of course. But in general term, we have this two right here. Those are product. And of course, we always ignore the solid and the liquid. Both of these are gas. So we just have H2 in terms of concentration. And then we have I2. And then that's the product. So what's the reactant? We have HI. But look at the coefficient there. That coefficient becomes the exponent. And that's it. It's not easy for the equilibrium constant. Now, what is the concentration of HI at equilibrium? And this is represented by here. So if we look at this graph, where does equilibrium really happen? Of course, all you have to do is trace back this line right here, going across like this, and you know that this is a concentration of HI, and of course, in this case, the concentration of HI at equilibrium is equal to 0.80 m. There you go. Isn't that easy? So by looking at graph, you can determine the concentration of any substance if it's drawn in at equilibrium. All you need to look is where does the concentration stay the same over time. Now this is where it gets tricky, okay? That's when we have to calculate for the other part of the reaction where it's not given in the graph. Because if you look at the graph, are we given information about hydrogen and iodine at all? No. So we have to solve for it. And the method to solving for this is something called the ICE table. So ICE table. So basically you can make a table ICE. Now the ICE table basically starts with, of course, you have your balanced chemical reaction. So let me rewrite that again. 2HI. And that's going to be reversible. H2 plus I2. Okay? Now, of course, I'm not going to make a table. That takes too much time. But the ideas of the ICE table is that you always start with your initial, which is at the beginning right here. Okay? Your initial. That is your initial. Of course, we have no product at all. But we always have your reactants right there. So the ICE is initial. So we have a balanced chemical reaction. Now we're going to have your initial. Initially we have reactant. Well, in this case, what is our initial? Well, let's write ICE. Our initial is that we start with a 1 molarity of HI. Okay? But, of course, we can represent that by 1 molarity. So very important, this is expressed in terms of molarity. Okay? Very, very important. Because we are looking at concentration. It just happened in this case is 1 mole per 1 liter. That's why we have 1. And of course, do we have any concentration of the product? Of course, it's 0. Because we don't have any product when we're starting our chemical reaction. But over time, what's happening is that there are changes. That's why we have the letter C. But do we know exactly how much being changed? Of course we don't. So we have to use a variable. And the common variable that we know is X. So we have an X amount being changed. Okay? So we know that over time that we're going to add some product to it. That's why we call it plus X. The same thing over here. But why am I plus only 1X instead of 2X or 3X? And that's because the coefficient here is 1. If this were to be 2, it would be plus 2x. If this would be 3, it would be 3x. So this is based on the coefficient, okay? So very important. Now, in most cases, you would know what happened to the change in terms of the reactant. It will tell you. Well, in this case, it doesn't tell you in terms of within the question, but it tells you that. Look at this graph right here. Where are we starting from? We're starting from the concentration of 1 m, okay, or 1 molarity. Don't get confused with 1 mole. It just happened to be already written in liter. That's why it's 1, okay? But look what happened. At equilibrium, now we have 0.8. See how that? So what is the change? Of course, from 1 to 0.8, that is minus. So of course you see a minus on the reactant now, because that's the changes. So minus 0.2 molarity, okay? See how that works? Or, what if we don't know what it is? Let's assume that we don't know, okay? Let's assume that we don't have the graph. What are we going to use? Of course, it's going to be minus 2x right there. Okay? Let's assume that we know that at equilibrium, the reactant concentration is 0.8, okay? But we don't know anything about the change. assume that we don't know that part. Let's just solve for that. So notice how I minus 2x because of the coefficient there. Now at equilibrium, we figure it out, or usually it's given to us. And at equilibrium, of course, we will combine the initial and the change together. So in terms of x, so we have 1.0 minus 2x. Notice how I combine this together. We have your initial and then your change, which is your initial here minus the change, and giving us the values of equilibrium for this reaction, okay? And the same thing in this case. But on the product side, what you have here is going to be 0 plus x. Remember, these are plus because we are making product from the reactant. That's why the reactant side is minus. So the product side is plus. So it's the same thing over here, 0 plus x. Well, we don't write that 0 plus part, so we can just write x. Does that make sense? But in most cases, the question will give us the values of equilibrium of the reactant, so we can solve for it. But based on the graph, we can actually determine that as 0.8. So what does that mean? That tells you that right here, okay, is actually also equal to 0.8 molarity. So 0.8 molarity. So how is that important? I'm going to remove the m here to show you that we can actually solve for x if we combine this together. So 0.8 equal to 1 minus 2x. Now can you solve for x? Okay, that's pretty easy. You just bring over here and you solve for x. Well, let me do the math for you just because you struggle with it. So what we have here is 0.8, okay? We bring over, you have minus 1 equal to negative 2x, okay? And let's do the math. I want to show you on a calculator so you can do it later on. 0.8 minus 1 equal to what? Negative 0.2. There you go. Equal to negative 2x. And what is x equal to? Of course, you divide both sides by negative 2, and divide by negative 2, negatives right there, and giving us x equal to 0.1. So that's x. So now we know what x is going to be. We can actually put in there, which is equal to 0.1 or 0.1 molarity. And since this is also x, this is also equal to 0.1 molarity as well. So now we know the concentration of the product at equilibrium as well as the concentration of reactant at equilibrium. So this is usually given to us right here. Let me write that 0.8 molar. Let me write that 0.8 molarity again. So these are the concentration at equilibrium. Now do you see the beauty of this ice table? So let's go back to C. Determine the equilibrium concentration of hydrogen and iodine, which we just did. So for H2, the concentration is equal to 0.1 molarity. And for iodine, at equilibrium, the concentration also equal to 0.1 molarity as well. Isn't that easy? Then lastly, what we have here is calculate the equilibrium constant for the reaction at 700 K. So we already know the equilibrium constant is right there. So all we have to do is substitute it in. But before that, let me rewrite it again. So we have H2 I2 I over HI exponent to 2 or to the power of 2, okay? And all you have to do is just plug it in from your equilibrium concentration. What we have here is hydrogen is 0.1, iodine is also 0.1, and over HI, which is 0.8 squared. And we just plug this into the calculator. We have 0.1 times 0.1 divided by, I would like to group everything on the bottom with parentheses there, 0.8 to the power of 2. And what do we have in the end? We have 0.0 0.156, and that of course can be rounded to 1/6. Let's try another problem. Here we have a 0.125 mole sample of N2O4 is introduced into a 1 liter. This is very important, okay, as well, because if it's not 1 liter, you have to solve for that molarity. So it's important. Container and allowed to be decomposed at a given temperature. When equilibrium is reached, the concentration of N2O4 is right there. So that's very important. This tells you that is your initial. That's how much sample you have at the beginning. But at equilibrium right there, okay, we have this concentration of N2O4. And that is related to that, okay? What is the values of equilibrium for this reaction? Well, first of all, is this equation balanced? Yes. So it is very important, and we are going to introduce the ICE table again. So ICE table. Beautiful, isn't it easy? Well, our initial in this case is 0.125. I'm not going to write M again, okay? That's too much work. So what we have here is 0.125. That's our initial for the reactant. And that reactant, of course, is going to make the product. Well, initially, you're not going to have any product, so we have 0. Over time, now you see the change. We're going to express the change in X, of course. Well, we don't know how much it's going to change, but we know that it's going to change somewhat. So we have minus X. There you go. Isn't that easy? So for the change on the reactant, you know that the reactant's internal concentration will decrease by a values of X. That's why we have a minus. But on the product, instead of decreasing, you have concentration now become products. We have plus X. But how many X specifically? Notice how the coefficient there, because it's a 2, we put 2X. There you go. Isn't that easy? Now at equilibrium, we also express in terms of X as well. We know that we're starting from that amount, 0.125, and we have 0.125 molarity minus X. So we combine them together, right? So we initially, the change will be minus, because we are using it to make the product. But on the product side here, we will have 0 plus 2X. But we don't write about 0 plus, we just put 2X. Well, now I told you before, there's always something that's given to you about equilibrium. Well, in this case, it told us that at equilibrium, this concentration right here, it's actually equal to 0.0750, okay? So we can express this in terms of an algebra equation, right? So we can solve for X. So let me do it on this side right here for you. So that way you can see how the math works. So 0.125 minus X equal to 0.0750. What is X going to be? Of course, minus X. And we bring this over here, okay? So we have 0.0750 is now minus 0.125. So let's plug this into a calculator, okay? So we have 0.0750 minus 0.125, giving us negative X equal to 0.050. And of course, X will just be 0.050. So we solve for X. 0.050. Isn't that easy? Now, keep that in mind. This is not equal to that right there, okay? The equilibrium concentration of N2O4 is this one. But with X now, we can solve for that. All you have to do is just plug it in, which give us 2 times 0.050, which give us 0.10. And that is the concentration of NO2. You see how that works. To solve for the equilibrium constant of this reaction, we need to express K. So I'm going to write that right here, okay? K, of course, is product over reactant or internal concentration. We know that NO2, and always remember to ignore the solid and the liquid. So because the coefficient there, that becomes an exponent. And then over here we have N2O4. Okay, now we just plug it in. We know that NO2 is equal to 0.1, so we have 0.10 square, and then that would be over what? That is given to us in the problem. Remember, don't get tricked by this problem, which is 0.050. And all we have to do is just plug into the calculator. 0.1 square divided by the bottom part, which I like to group with the parentheses right there, 0.0750. And our answer is 0.133. Isn't that easy? And that would be our K right there.